So what is the most important thing in bagging? The sampling. Sampling is random and done with data with replacement method. Done with data with replacement method. This is the first thing. Sampling is random and done with data with replacement method. Okay. So what about boosting? Sampling is random but wrong predictions of previous model are given top priority, right? They will be added first and they are given top priority, and in some XGBoost and all they are given weightage also. They are given weightage. So in a simple grading boosting, they will be given priority in the sense they will be the first to go to the next sample. And in XGBoost and LGBoost and CADBoost, they will be given more weightage. The wrong classifications will be given more weightage, and rest of the observations will be given less weightage. That is one thing. What is the second difference? Trees are built independently. Sorry, trees are built parallel. Parallel building of trees, as each sample is independent, right? Each sample is independent. Each sample is independent. Trees are built parallelly. Here what happens in boosting? Trees are built sequentially. Each tree is dependent on previous trees per sample. Per sample. All right. Bagging overcomes the overfitting problem. Right? I told you now the important aspect why random forest was created is to overcome the overfitting problem that happens in the decision tree. Too good to be true, having extra thing. What do boosting do? Boosting tries to reduce bias. Boosting reduces bias. Boosting reduces bias. Now, in bagging, each model receives equal weight. That means each tree receives equal weight. Each tree receives equal weight. And in case of boosting, trees are weighted according to their performance. Trees are weighted according to performance. Trees are weighted according to performance. Performance is how accurately they are predicting or not. Now, if the classifier is unstable, or high variance, then apply bagging. If classifier is unstable, then we will apply bagging. Similarly, if the classifier is stable and simple, then we will apply boosting. We will apply boosting. And bagging aims to decrease variance, not bias. I'll just discuss what is bias and variance. That is very much important. And boosting aims to decrease bias, not variance. So these are the major difference between bagging and boosting. Okay. All right. All of you understood the difference between bagging and boosting? Data? Not random. Yeah, random. Here also boosting also same thing. See, the procedure is same thing. 65% of the observations randomly selected, square root of number of variables randomly selected for both the models. For both the models, 65% of the observations randomly selected, square root of number of variables randomly selected. The only difference is in boosting, what happens is wrong predictions will go to the sample first and the remaining it will take from the randomly selected from the rest of the data. Okay, so only wrong predictions keep on repeating more number of times. Whereas in bagging, every time the sample is taken, it is taken from the whole data. So observations and variables will repeat multiple times. The only difference thing is boosting gives more weightage to weak learners or wrong predictions. That is the only difference between both of them. Second is bagging is parallel building of trees because each sample is independent. Boosting is sequential building of trees. Each sample is dependent on previous trees. Another thing is if the classifier is unstable, apply bagging. If the classifier is stable, apply boosting. When I say stable, not too much of accuracy difference. Like on training data, you got 90%. On test data, you got 75%. That means the classifier is unstable. If the trained data and test data have closer accuracies, then it is a stable classifier. You can use boosting models there. And the second thing is bagging aims to reduce variance and boosting reduces bias. Right? Now let us understand this bias and variance. This is one of the, again, very important interview question. As you go into higher levels of data science interviews, lot of discussion happens on this bias and variance. Bias, variance, and trade-off. You need to go for trade-off between these things. So all of you can see the font. Is it okay? This is okay? Bias, variance, and trade-off. Trade-off means you have to balance them one another. Now, the objective of data science is prediction, and we get something called prediction error. The objective of our models is to predict. Whether it is a classification model or a regression model, our job is to predict. Right. So when you are predicting, there will be some sort of error. Because statistics, we say 95% confidence level, 5% error. Similarly, very rarely or in real-time data science, it is impossible to get 100% accuracy or adjusted R square of above 90%. Because they're all hypothetical textbook situations, you get that thing, but in real-time data science, you will not get it. So you have to balance out this bias and variance. Now, prediction error. Zoom పంపించేసాను. Zoom ఇచ్చేసాను. Record చేస్తాను. So prediction error has three components. There are three components within prediction error. The first one is bias, the second one is variance, and the third one is irreducible error. That means you cannot reduce the error. Bias, variance, and irreducible error. Now, irreducible error cannot be reduced. Irreducible error cannot be reduced regardless of what algorithm you use. So irreducible error cannot be eliminated no matter what algorithm is used. That error is always will be there in your prediction. Now this error comes from framing the business problem and caused by unknown factors and variables. See, classic example of irreversible error is COVID-19. When you are talking about loan prediction models or credit card default prediction models 2 years back, did we have a variable called COVID? Now, what did COVID do? Loan default rates went up, credit card default rates are very high. Even people with very, very strong credit score and very, very strong jobs also, because of their salaries got delayed or salaries got deducted into half, all those people failed to make their payments. So there will be an irreducible error. There will be an unknown factors which you have to take into consideration in your model. COVID was a big lesson for all the credit risk models, right? Now, the most credit-worthy person also was in trouble because of liquidity issues. Government salaries, government was giving half salaries to their employees, right? Some people gave, some governments didn't even give salaries. They delayed the salaries because they were not getting tax revenues. So banks were told to ignore defaults by these people. Right. Then RBI sent saying that don't force people to pay. We will not treat them as NPAs. Let them default and they'll pay at later stages. Private companies, half salaries or no salaries. Some companies paid only salary, no TA and other allowances were paid because people are not working. So all these things are there. Irreducible error will always be there in your model, which you can't know it exists because we didn't know COVID existed, right? COVID is a reality now, not 3 years back. Now all credit models have to take into considerations pandemics. Okay, there is a chance pandemic will come, so we have to take pandemic and give weightage to pandemics in our credit models. That is what Now people are doing it. But prior there was no chance, right? So irreducible error is of that nature. Now, what is bias? Bias are simplifying assumptions. Bias are simplifying assumptions made by a model to make the target function easier to learn. So bias are assumptions made by the model to make the target function easier to learn. Assumptions. We talked about assumptions basically, or we call them parametric algorithms. Parametric algorithms like multiple linear parametric algorithms like multiple linear regression. Right? There are many assumptions for multiple linear regression, right? Close to 8 assumptions are there. Normality, exogeneity, linearity, no multicollinearity. So these are all biases. When you are building a linear regression model on a data, the model will assume that all these assumptions have been met or satisfied. Right. Similarly, binary logistic regression also has lot of assumptions, right? Lot of assumptions are there here. So when you have these prior assumptions, that means they are all nothing but bias. Bias are those assumptions that we make at the beginning of the model to make the model to learn easier. These assumptions, like in multiple linear regression, normality, multicollinearity, linearity, exogeneity, all these things are assumed to be satisfied if you run a multiple linear regression model. That is a bias. Okay, particularly in linear models, you will see this bias. Particularly in linear models, you will see this bias. Assumptions. Parametric algorithms means algorithms with assumptions. Non-parametric algorithms, they don't have any assumptions. KNN is non-parametric, decision tree is non-parametric. So parametric means there will be assumptions. Non-parametric means no prior assumptions. See, linear algorithms have high bias, which helps them to learn faster. So why do you think the bias is inherent? Because linear algorithms want to learn, if there is a bias, they learn very, very faster. The process of learning the thing is faster. The problem is low predictive performance, on complex problems that fail to meet assumptions. So linear regression algorithms fail on large scale data sets. When data is very large in terms of rows, in terms of variables, they tend to fail. Because as your sample goes up, your what you call skewness, kurtosis also will go up. On a smaller samples, it will be less, but on a very large sample, you can't control them, right? They're very, very huge outliers will also appear on large scale data sets. So that is what happens with bias. Now, low bias means less assumptions about target function. High bias means opposite. More assumptions about target function. Now, target function is the equation here. What I mean by target function is the equation, right? We use the equation to predict. In regression, what is the output? Y is equal to intercept plus beta 1 x1, beta 2 x2. That is what we use to predict. That is called target function. Or you can also call target function as the function that reduces the error, RMSE, root mean square error. Sigma y minus y hat whole square divided by n minus 1, square root of root mean square error. Now, low bias machine learning algorithms. Low bias machine learning algorithms. Low bias machine learning algorithms, decision tree, KNN, and SVM. You all know SVM, right? Support vector machines. KNN is neighbors and support vector machines. High bias machine learning algorithms. Yes. Linear regression, logistic regression, and linear discriminant analysis. This is also linear discriminant analysis. Got it? So this is the background of bias. Bias are the assumptions made at the beginning of the model. These assumptions help the model to learn faster. But these assumptions also create problem when the problem is complex. When you're trying to build complex models on large scale data sets, on big data sets, then these models tend to fail. Bias. Okay. Any doubts in bias? Now let us look at the other error, variance. What is variance? The amount that estimate of the target function will change if different training data is used. If different training data is used. The amount of change in the estimate if you change the data. It can be test data, it can be subset of this training data, cross-validation. Like I told you, cross-validation is nothing but you subset the training data into smaller randomly subsetted samples and you build the model and you cross-validate the error. Why do we do? To check the variance error. The reason why we do cross-validation is to identify the variance error. Variance error means how the accuracy or how the RMSE changes as you train the model with repeated samples of the data. You train the same model with repeated samples of the data. That process, we get the variance error. We call it as cross-validation. Machine learning algorithms are sensitive to specific changes in the training data As and when the new data is given and the data is having, say, outliers or skewness, which was less in the training model, then obviously your training data error will be higher, right? You didn't have that much of skewness when you're training the model, but the new data which you're giving has skewness or outliers or kurtosis, then the model will drastically change. The performance of the models will drastically change. That is why whenever you're trying to do the test data, you also check the test data for the same assumptions which you have made in the trained data. Like you check the skewness of all the numeric variables. We do it in trained data. We try to check correlations between variables, right? In trained data. So same process you have to repeat on test data also. If you are seeing a lot of variance when you are doing the test data things. So first thing, when there is a variance between train and test data things, you have to go and check the variables. How will you check? If it is a numeric variable, you check for skewness and kurtosis. Correlation, again, numeric variables, correlation and covariance. For non-numerics, you will do the frequency counts and see whether the balance or imbalance are happening in that particular variables. By imbalance in that particular variables might be causing the problem. So that you have to check. Now, low variance. Low variance means small changes to the estimate of the target function with changes to training data set. High variance, large changes. You will see very big change in terms of estimate of the target function. All right. Now, non-linear algorithms. The one thing you need to understand is this again competition. Why do decision tree? You know, decision tree has high variance, right? One of the most, whenever people ask what is a high variance model, you can simply say decision tree because it definitely overfits. And it's a non-linear algorithm. It's a non-parametric algorithm. So non-linear algorithm, typically non-linear machine learning algorithms have a lot of flexibility. Decision tree is one of the easiest to use. It works with missing values, it works with outliers, right? It have a lot of flexibility. But what is the problem? Have high variance. But have high variance. Decision tree works with outliers. Decision tree works with missing values. Decision tree works with any type of variables. It identifies variable importance also, right? It can work on any type of data. High categorical variables, less numeric variables, or high numeric variables, less categorical variables. Any type of data, decision tree will work. The flexibility is there, but the problem is variance. Decision tree is an example. Decision tree is an example. Now, let us look at the low variance machine learning algorithms. Low variance machine learning algorithms. So low variance machine learning algorithms are opposite to bias. Linear regression, logistic regression, and linear discriminant analysis, LDA. High variance machine learning algorithms. High variance machine learning algorithms are again opposite decision tree, KNN, SVM. Right? See, multi-tree models, sensible models work with, they balance this variance and bias because you are building multiple trees there, right? So that's why we don't come into that part. They are in between models, random forest and GBMs. They are in between models, right? They balance it out because multiple trees are being built, right? With different sets and combination of models. So all the models will take all the combination of high variance and low variance and higher bias and low bias into consideration and build it. And the goal of any supervised machine learning algorithm is to achieve low bias and low variance, which is very difficult to achieve, right? So the ultimate is you have to get a trade-off between bias and variance. The best fit model will be low variance and low bias. But in reality, it is very, very difficult to achieve this trade-off or balance because linear models have high bias, low variance. Basically, what happens is in linear models, what we have high bias, low variance, right? And in non-linear models, what happens? Low bias, high variance. It's a trade-off. There is no escaping from this thing. You have to find a middle path. So it's a trade-off. You have to get it. If you try to increase the variance, it decreases the bias. If you try to decrease the bias, it increases the variance. So that is the value, that is what we have to understand in terms of trade-off between variance and bias. Now, there is a classic what to call graph which we use to understand this. So the blue is the bias, the green is the variance, and red is your generalization error. It has to be somewhere in between. The left side of it will be underfitting zone, the right side of it would be overfitting zone. See here, in underfitting zone, you have low variance, high bias. In underfitting zone, you have very low variance, but high bias. Whereas in overfitting zone, you have high variance and low bias. And you need to find the middle path. That will be your best fit model. How do I identify? Cross-validation. Cross-validation, k-fold cross-validation, repeated k-fold validations, repeated testing with different subsets of data or different sampling methodologies will help you to identify this problem. So the bias versus variance trade-off is a very, very important thing you need to understand. You cannot eliminate both of them. You will try to minimize them as much as possible. But in reality, if you try to minimize one, the other will go up. If you try to minimize the other, then the one which you are focusing will increase. So you have to have a trade-off. Underfitting zone is low variance, high bias. Overfitting zone is high variance and low bias. That also very important interview question. So underfitting zone means low variance and high bias, and in overfitting zone, opposite, high variance and low bias. So all of you understood the importance of bias and variance in machine learning algorithm. This is very important. Bagging, boosting. So what does bagging do? Bagging decreases variance, but not bias. Whereas boosting decreases bias, but not variance. And you always have to have a trade-off between variance and bias. You cannot avoid them. You cannot ignore them. This is the theoretical context of bias and variance, which you need to understand in the context of overfitting and underfitting. Right? Overfitting means train data, you will get 99% accuracy. On test data, you get 70% accuracy. The variance is very high. Similarly, you get an adjusted R square of 95 or 94% on train data. The adjusted R square falls to 65 or 70% on test data. Again, overfitting problem. Underfitting, the minimum is what? 0.60 R square in regression, 0.70 in classification. If you don't reach this minimum threshold, that means you are in a underfitting problem. So we need to understand, if it is underfitting, that means the bias is high, but variance is low. Okay.
So then last class we applied say equal to 5 that 0.935 array. So that gives
it's okay. That's what I told you. No random bagging, no, but that's the balancing method. So on a train data, you got 99 or 97% accuracy, 99. On test data, repeatedly 93. That's a constant, no, stable model. It's a good model, stable model. Had it gone down to 80% or something like that, then we are worried. As long as it is about 90%, we need not worry about that model performance. It is a stable model.
when like on HRM analytics, that region is more than like so many categories. So we applied their level. But when we are applying dummy encoding, when we will apply dummy encoding, it is not going to work.
See,
more than two categories.
Classification imbalance is a problem. It's not more of the variable issue in classification. Classification is the target variable, imbalance is the biggest problem. Like how we have skewness problem in dependent variable in linear regression, which affects your model. Here in classification, rather than independent variables, the dependent variable imbalance is biggest problem. So before we go and check our independent variables, let's check our dependent variable balance. If your dependent variable is balanced and still you're getting, then you go and check your independent variables for the imbalance in the categoricals or skewness or kurtosis in the numeric variables.
So sir, in that case, dependent variable is stable.
No. The HR analytics 50,000 to 4,000. It's a classic imbalance problem.
Yeah.
See, promotions in an organization is always less. 10% of the employees only will be get promoted. Do you promote everybody in your team? Only 10% should be promoted. That is a started rule across the levels of organization. Only 10% of them will be promoted at all levels. That means 90% will not be promoted. Imbalance.
It's a
Natural imbalance. Credit card default. Will all your customers will default? 10% of the SBI customers will default, or in case of HDFC, which is a private bank which takes more cautious predictions, they may have 6% or 7% fraud rate. They have not have zero. Zero fraud rate can exist, no, right? It cannot be zero. There will be defaults. Now, how much the defaults will be single digit default or a double digit defaults depends on the banks and their strategy. How they issue the cards. See, dummy encoding must be used in regression. I told you very clearly there. Regression is affected by the bias on the larger numbers. So for regression algorithms, you have to do scaling on numeric variables, and you also need to create dummy categoricals. In logistic in classification models, not required. Label encoding is enough. In regression, two things are required. Dummy encodes of the categorical variables and then scaling of the numeric variables. If the variables are in different mathematical units. Standardization is preferred. Standardization is preferred. Normalization is like a brute forcing. You are brutally forcing them to 0 to 1. Normal, what you call narrow range, right? Sometimes when you force the thing into narrow range, your models will behave not well. So we prefer scaling. Even in clusters also, we prefer scaling. For all distance-based algorithms also, if you scale the data, the distance calculation will be easier. Now normal
mean equal to 0 from that axis it is going to be
yeah, x minus mean by standard deviation, right? So mean 0, 1 standard deviation.
From that axis it is
up and down. So you'll have negative as well as positive values. Whereas in normalization, all will be positive values and 0 and 1. Okay, got it, all of you? Now, since we are also discussing overfitting and underfitting, let's complete that part also. Overfitting versus underfitting. This is also very important interview question. Now, what is underfitting? Underfitting is where the ML algorithm fails to capture underlying trend of data. So underfitting is where the machine learning algorithm fails to capture the underlying trend of the data. Simply saying, the ML algorithm does not fit well on the data. The ML algorithm does not fit well on the data. It generally happens when data is small or not enough. When you don't have enough data, we have this underfitting problem coming into picture. Now, underfitting can be avoided by increasing data and reducing features or variables by feature selection. By feature selection or reduction of variables, you can reduce the underfitting. Then techniques for reducing underfitting. Techniques for reducing underfitting. Increase model complexity. Rather than, like I told you, na, if your linear regression does not well, we'll go to the next complex model, which is decision tree. Next complex model, which is random forest. Next complex model, gradient boosting machine. Next complex model, neural network. Like that, we have to go ahead. Increase the complexity of model. Increase the number of features by performing feature engineering. Oh, not increase. I think this is wrong. Decrease, right? Decrease the number of features or variables by performing feature engineering. Feature engineering means do a correlation analysis and then reduce. Select k-best models based on k. If you are all or categorical variables, select k-best method is there, which uses chi-square among the variables to identify the important variables. Similarly, Gini is there, information gain is there in decision tree models, where you get important variables, feature importance will be given, right? That we can use for reducing the number of variables. Remove noise from the data. Remove noise from data. When I say noise, what is noise? Noise means, you see, skewness, kurtosis, outliers. Skewness, kurtosis, outliers, and imbalance in case of categorical variables. Right. So you have to remove the noise. If you are using neural networks or advanced deep learning algorithms, increase number of epochs. Increase the number of epochs or increase duration of training to get better results. So epoch in neural network means one full cycle of building the neural network and then adjusting the weights in the neural network such that error is reduced. So you first build a network. It's like linear regression only. You build a model neural network, feed forward network, and you predict. You will get an error. And backward propagation is the process where you try to reduce the error by adjusting the weights. This whole cycle, we call it as one epoch. one cycle of building the neural network and then backward propagating the same network, going backwards in the same network by adjusting the weights to reduce the error. When we do neural networks, that time I will discuss this in detail. Then comes our overfitting. Overfitting. Occurs when we train model with lot of data that has big noise, which leads to inaccurate estimates. So overfitting occurs when we train models with lot of data that has noise. Noise means skewness, kurtosis, outliers, and imbalance, which lead to inaccurate estimates. Non-linear and non-parametric ML models suffer from overfitting. Non-linear and non-parametric ML models suffer from overfitting. Techniques to reduce overfitting. Reduce model complexity. Reduce model complexity. Early stopping during training phase. Regularizations like lasso and rich. Use dropout in neural networks to reduce overfitting. Use dropout in neural. Dropout means at every layer you will ask to drop 20% features which have least importance. It will drop those variables which have low weightages or which have low coefficients or coefficients closer to 0. They will be dropped out. They will not be carried forward to the next layer. No, dropouts will be in 0 to 1. 10% dropout, 20% dropout will be. At learning rate, which is your gradient approximation, weight approximation is what we are talking about. Multiples of 0.01. So this is the underfitting, appropriate fitting, and overfitting. Got it, all of you? We discussed last one in Ridge, right? No, we have not discussed regular resolution. We have not got into that place. Now, what hyperparametric tuning we are talking about? That okay, I'll explain.